This is A2Pure Maths. We are in Unit 6 and we're looking at sequences and series, and we're now going to take a wee look then at geometric series. So the previous one was arithmetic series and it was the same gap each time, so you were adding on 3 each time or something like that. Geometric series is formed by multiplying the previous term by a constant that's called the common ratio then, which is going to be r. This one here you can multiply by 2, for example, 1, 2, 4, 8, 16. Here we're timesing by a third, half, a sixth. A sixth times a third gives us an 18th, and 18 times a third gives us 1 over 54. Here we're timesing then by minus 4 each time, 2 minus 8 plus 32 minus 128. So in general, what do we have? We have our first term, which we start with, it's a, and we multiply it then by the common ratio. So that's the next second term then is AR. The next term then is you times by r again, so it's a times r, so it's AR squared, times by r again. So the powers of r then just kind of keep going up, and you end up that AR to the n minus 1 then is going to be our nth term. So why is it n minus 1? Because this is my first term, second term, and a bit like our arithmetic series with the d, if you remember, the fourth term is cubed, the third term is squared, so it's 1 away, so it's AR to the power of n minus 1. So our way of finding our nth term then is u of n is AR to the n minus 1. We had a wee trick last time, and we need to be able to do it for the exam. The same for this, for finding the sum of the first n terms. If you remember, for the arithmetic series we wrote it out forwards then backwards. Once you added them you get the same term each time. There's a similar wee trick we need to learn, so let's take a wee look. Almost talk ourselves through this one. So the sum is obviously going to be a plus AR plus AR squared plus all the way up to AR to the n minus 1. The wee trick here is multiply through by r, so you get r s of n. So that gives me AR plus AR squared plus AR cubed plus AR to the n. So what am I going to do? I'm going to do this, take away this. Some people want a wee line in here. We can do that if it helps, and put a subtract sign so people to see what's going on. So we're going to subtract this here. So my next line is going to give me s of n, that's the sum of the first n terms, minus r s of n. And again, can you see what's going to happen? You do all of this, take away all of this. So this one and this one is going to cancel out. This one and this one is going to cancel out. This one would cancel out with the next one, and of course then this one would cancel out with the previous one there. That one's a wee bit harder to see. I hope you can see where I'm getting that from. But all we're left with then is a, and then take away AR to the n. You might want to work your way through that one a wee bit again to see where it's coming from, but that's what we have. We're trying to find the sum of the first n terms, so we need this wee s of n bit on its own. There's two of them here, so I'm going to factorize it out. So my next line is s of n upon 1 minus r, a minus AR to the n. I'm then going to factorize out the a here. Sorry, made a mistake here. Shouldn't have an equal sign just yet. S of n 1 minus r equals a upon 1 minus r to the n, and then my s of n, and the formula then that you need to be able to derive but also know and use, is going to be that. So that's my formula for the sum of the first n terms. S of n equals a upon 1 minus r to the power of n all over 1 minus r. Okay, example 1 then. In a geometric series, u3 is 32. That means the third term is 32 and the sixth term is 4. Find a, r and the sum of the first 8 terms. So our wee formula is u of n is AR to the n minus 1. That means we know u3 would of course be AR squared. You see where I'm getting that from? It's 3 minus 1 there. And then U6 is AR to the power of 5. If we do a wee clever move here, which is U to the 6 divided by U to the 3, we get AR to the power of 5 all over AR squared. So what happens there? The A's cancel out, that square cancels with that, and they end up with an A cubed. That's also equal to 4 over 32. So what do I know? I know that R cubed, because that's what I'm left with here, is 4 over 32. That cancels down then to an 8, which is handy. Taking the cube root then, that means R is a half. So we've got that bit, we've found our common ratio. It's multiplied by a half every single time. Let's sub it back into one of these and see if we can work it out. So we know that AR squared equals 32. That means A upon a half squared is 32. A half squared, of course, is a quarter. So a quarter of A is 32, and that means A then must be 128. So we're good to go. We've got our first term, it's 128, and our common ratio is a half. So it's half in each time. These are powers of 2. You can probably spot that anyway. And it says then find the sum of the first 8 terms. So we know A is 128. We know R is a half, and N then is 8. So S of N is A upon 1 minus R to the N all over 1 minus R, and our S of 8 then is 128 upon 1 minus a half all to the power of 8 all over 1 minus a half. So can we tidy this up? Not sure, but we'll try. 128, 1 minus a half to the power of 8. So let me think. 2 to the power of 7 I think is 128. So 2 to the power of 8 is going to be 256. So 1 over 256. And 1 minus a half, of course, then just gives us a half. So if you tidy that up, to be honest, if you kind of put it in your calculator, it'll all work out nicely for us. But you end up 1 minus 1 over 256, obviously 255 over 256. The 128 and the 256 cancel because this is double this one, and then divide by the half. You just end up then with 255. Okay, I'm actually going to leave question 2 for the minute until we've done our sum to infinity, because you need that first, so that's going to come up in a wee second. And we're going to go for example 3 first of all. And we can do this, it does need a bit of logs, but we should be able to work it out. So geometric series has the first term 27 and a common ratio 4 over 3. Find the least number of terms, fewest maybe, this series can have if its sum has to exceed 550. So let's take a wee look then at this one. What do we know? We know A is 27, that's our first term. We know our common ratio is 4 over 3, but we don't know our N, which is a bit problematic. So that's what we need to find out. But we do know we're going to set our sum of N up to be then 550, because we want to see then how many N's it's going to take to get to hit 550. Mine come out to be an even number, but we'll see because it's going to exceed then the 550. So of course I mean a whole number. A upon 1 minus R to the power of N all over 1 minus R. So let's start filling this in. It's awkward enough. 550 equals 27. 1 minus 4 over 3 to the power of N all over 1 minus 4 over 3. So let's try and start tidying this up then and see what we end up with. 550 equals 27. 1 minus 4 over 3 to the power of n. 1 take away 1 1/3 gives us minus 1/3. So that bit's okay. Minus 1/3, 20, this is whole thing here divided by minus. If you divide this here by minus 1/3, it just gives us a minus 81, makes this 3 times bigger. So we're then going to go 550 equals minus 81 upon 1 minus 4/3 to the power of n. We're going to divide then by minus 81. I need to be careful with the space I'm using here. There's still a fair few lines to go. 550 over minus 81 is 1 minus 4/3 to the power of n. And then, so I then want to do, I'm going to take this over to this side here. That gives me 4/3 to the power of n equals, and then 1 plus 550 over 81. So I need to add another 81 to that. Effectively then we're going to get 631 over 81. I hope you're still with me there for that. So we have an n here that we need to work out. It's to a power, so we're going to have to take logs in at both sides. So we're going to go log 4/3 to the n is log 631 over 81. And of course then n log 4/3 is log 631 over 81. N then is going to be log 631 over 81 all over log 4/3. We just want to put this into the calculator effectively. If you do that, you will get 7.135. So what does that mean? Whenever it's 7, it's not quite at 550 because it goes 7.135 terms to hit 550. So effectively we need 8 terms. So that'll be our final line then. Therefore, sum exceeds 550 when n equals 8. Okay, so we're going to take a wee look then at infinite geometric series and the sum to infinity. If it's infinite, it only works if r is in between minus 1 and 1. If r is bigger than 1, the sum to infinity is simply infinity. So if r is between minus 1 and 1, then each term gets smaller and smaller and smaller, and so eventually then it kind of comes to some sort of sum. Let's take a wee look at our original examples and see if we make any sense of this. I mean, if you add this, it's just going to go to infinity. You know, the numbers get bigger and bigger and bigger. But this one here, if you add a half and a sixth and an 18th and a 54, it actually gets closer and closer and closer to a number. It tends to a certain number as r kind of goes on and on and on. So it's the amount of terms. So it doesn't actually, you know, it doesn't like kind of add up to infinity. It doesn't eventually get there. So we'll work out that one in just a wee second. But let's see what way this formula goes and see if we can work it out. So what we effectively have, our n then is going to be infinity. So we're changing that. So sum to infinity equals a upon 1 minus r to the infinity all over 1 minus r. If you then do the ratio to the power of infinity, you know, if you do like say it's a half to the power of infinity, it just goes to 0. If you do a fraction to a really big power, it just gets closer and closer to 0. So effectively our sum to infinity is going to be a upon 1 minus 0 all over 1 minus r. So our sum to infinity then is a, because you just multiply that out, the 0 sort of makes it disappear, over 1 minus r, which is quite a convenient thing then to work out. Let's actually do it just for fun for this wee example. So we had a half plus a sixth plus an 18th plus 1 over 54. So our a here was a half and our r was was a third. So let's find our sum then to infinity. Hopefully the sums don't aren't too much from here. But we're then going to have a half on the top all over 1 minus a third. So it's going to be a half divided by 2 thirds. So how do you do that? If we times top and bottom by 3, so I'm going to mess this up. So we're going to go with half multiplied by 3 over 2. I think that's right. I'll check it in a wee second. So the sum to infinity, it gets closer and closer and closer then to 3/4. Finally, then we can go back to this example 2 because it involves a sum to infinity. The first 4 terms of a geometric series are 0.23, 0.0023, 0.000023, and so on. Find the common ratio. Well, I can see what you multiply this by to get this, but let's just kind of pretend we don't quite know. Let's look at our first term. A is 0.23, and then AR, which is our second term, is 0.0023. So if we do AR over A, we're going to get 0.0023 times 0.23. And that of course then gives us 1 over 100. So you're dividing by 100 each time. So your common ratio then, which is going to be R, because the A's obviously cancel, is 1 over 100. So that's our common ratio. That's that bit found. Part 2 then is sum to infinity. We've just done one like this. We should be okay. Our formula for sum to infinity is A over 1 minus R. So that's then going to be 0.23 all over 1 minus 1 over 100. So it's then going to be 0.23. Effectively, then on the bottom, 1 minus 100 is going to be 99 over 100 if you want, then 0.99. So one kind of tidies up quite nicely. If we times top and bottom by 100, you would get 23 over 99. So as you add these terms together, you're going to express the occurring decimal. 0.23232323. That's going to be then kind of 23 over 99. Sure enough, if you try that into your calculator, 23 divided by 99 equals, you get 0.232323. So that kind of gets us our sum there. Hopefully you see I skipped over a wee bit what we're actually doing there. As you add these up, you of course get 0.23232323, and so that's then why we're showing that.